This presentation is about the experiences we had with demand paging since we introduced this technology 2-3 years ago. Since then, the technology has matured, and we have more experiences with how to deploy it and learn some lessons and how it could be used. I'll start with giving some insights regarding demand paging. Then I'll do a brief overview of the APIs and development status, and conclude with some evaluation examples. So basically, when you do I/O, you grant devices access to buffers. For example, NIC transmit and receive buffers. When you do PCI pass-through, basically you grant the whole guest memory to your virtual function. Or when you register a memory region, you grant the device access to that memory region. During this period, typically, the device expects to have irrevocable access to the underlying pages. So, for example, from the moment you have posted a NIC receive buffer, and until actual data comes in, those buffers or pages have to be resident. So in that case, it's a rather short lifetime, and also it's relatively small buffers. But in the cases such as PCI pass-through and memory regions, we're talking about very large portions of memory which could be pinned for a very long amount of time. So because of that, there are two main prices to pay because of this long time pinning of memory. The first is the price of pinning itself, and that usually pertains to virtual memory optimizations. So there are a bunch of virtual memory advancements that were made over decades that once you pin memory are no longer available to I/O buffers. For example, you can't allocate pages on demand after you map some file. You can't do copy and write when you spawn a new process and want to register some portion of it, and maybe you're initially accessing a very small amount of that virtual memory. You can't migrate between NUMA nodes once you pin the memory. So this is one serious drawback. And a related issue is that it complicates the administration and deployment of such direct I/O applications. So you have to grant special privileges to pin that many memory. Often you have to have worst case planning. And again, obviously you can't pin more than you have physical memory in the machine. Another price, which might have been forgotten in this community, but it's very hard to people that come from the outside, is that of memory management. So when you register memory, even if your memory regions are not pinned, you still have to track which memory is registered and which isn't. So these kinds of application memory pools that are registered, they just put aside decades of memory management expertise, right? I mean, the operating system is continuously optimized. The workloads change, technology changed, the correct work points are changed. And this is constantly being updated and optimized by the community. The same goes for the C runtime, right? Malloc having different arenas for threads. There's a lot of know-how going into that. And after that, you might have libraries that have specialized pools. So once you're telling the application, you can't use all that. You have to manually manage your memory pools. You're just putting all these applications at a disadvantage. So when people come to RDMA, there are basically two, I'd say, main difficulties to work with RDMA. The first is asynchronous I/O, and the second is memory management. People are pretty much used to working with asynchronous I/O. I think it's very common a matter of holding reference counts to buffers in certain layers of applications, especially with more advanced languages. So just holding another reference there until I/O is complete is easy. But there is no way around memory management. And getting it right requires a very complex expert programming skills. And the resulting code is extremely complex, and this is for people that have the knowledge of this community. Now, think about newcomers that want to have some application and port it to RDMA. It's practically a non-starter. People have tried to mitigate these costs. I just mentioned here two main techniques, but of course there are all sorts of optimizations and ways to interleave these two techniques. The first is using a fixed pool of buffer. So you have your application workspace with all your data structures, and you have your communication library with some pool of pin buffer, and then you just copy in and out data as you communicate it. So this works for very small messages. It's efficient, but it has significant costs when large messages are involved. And even then, if you didn't estimate right the sizes here, you might need to grow these buffers or release them, and that is also hard. The second method is, let's try not to burden the application with these kinds of considerations. So we have the application doing any kind of allocation it's used to do with all the aforementioned optimizations. And we try to transparently pin buffers and optimize through a notion called pin down cache. Over the years, there's a lot of versions and papers on this. There's Firehose, there's pin caches that only grow, there was can be released, a lot of implementations. And the problem here is, again, it's very hard because the allocation is done right up here. There could be multiple layers of libraries and between the application allocations and this communication library that tries using a bunch of heuristics to guess how to get the pinning right. In addition, the number of ways you can allocate in free memory is pretty large. And this is just system calls in C. I'm not mentioning here all those C++ operators and other languages. And in order to get this caching right, you have to track all these allocations and freeze. You have to optimize, which is a bunch of heuristics. And it's very hard. So this is where demand paging comes in. And I'm going to show you how, using two features of demand paging, we can basically get it all. We can, on one hand, we can leverage all the transparent memory management that we get from a runtime. And on the other hand, we can do direct I/O with the performance that we're used to. So the first is the notion of demand paging itself. And the idea is that we allow the translation pages, the translation tables of the memory regions to contain non-present entries. So by doing that, we have memory regions that are actually never pinned by the operating system. Pages are paged in when the HCA needs them, and they're paged out when they're reclaimed by the operating system. And this basically eliminates the price of pinning, because now that we don't have any pinning, the virtual memory system can do whatever it wants. So as a brief demonstration of how demand paging works, assume that we have here a process address space. This is the MMU of the processor. This is the I/O MMU of the device. Again, I'm not going to the specifics. IOMUs can be on the I/O device, could be the chipset IOMU, can be anything, but the idea is the same. And let's say that I have a mapping to this page frame number 4 here. And assume that we have two accesses coming up. One is a change in the PTE by the processor, and the other is an access by an RDMA operation. And once we have this change, we invalidate the entry here of the IOMMU, and it could be that this doesn't work very cleanly. Okay, it could be that a microsecond later, an access comes in and incurs a page fault. So what's going to happen is that the HCA is going to raise a page fault of the device. We're going to get that translation, and we're going to fix that this translation entry. And after that, the access can continue. So the promise is that we're going to keep the IO virtual address mapping identical to the process virtual mapping at all times. And this basically removes all the consistency issues between pin-down caches and what the operating system is doing. In terms of the implementation, we have here a cooperation of the InfiniBand core system and the device driver. I'll start with two flows. When we have a page fault, it's the device driver that raises an interrupt. Again, this is not a page fault because of a CPU access, right? It's a page fault because the HCA is trying to execute some, for example, incoming RDMA write, execute a transaction. So it's a regular interrupt by the device. And what the driver is going to do is it's going to translate the details of the interrupt cause into a memory region and offset into that memory region. And then it's going to request the InfiniBand core to fill in the missing pages. And once the pages, we get the DMA addresses back, then we feed it to the device and we tell it to resume the transport operation. On the invalidation side, so invalidation starts by a call from an MMU notifier that tells us that something has changed in the process address space. And the first entity that catches this invalidation is the InfiniBand core that resolves this invalidation with a given address and finds all the overlapping memory regions that are affected by this invalidation. And in turn, we get the specific keys and offsets which the device needs to invalidate. So this is a synchronous operation. We invalidate the device TLB, and after that, the operating system can resume what it's doing. Okay, so that was how demand paging works. It allows you to have large memory region, which is not pinning memory, but it doesn't fix the problem of tracking which memory to register. And this is where the global address space key comes into play. So imagine that we can register the whole address space of a process using a single key, right up from the first bytes that catch null pointers and down to the stack. So we have an MR which covers a lot of unmapped virtual address ranges, right? I mean, the address range is huge. It's very sparsely populated, which is also kind of weird when you think of regular memory regions, because a lot of these portions don't even have permissions yet because they're not mapping any memory. But the checks are done at a different stage. So when you're actually attempting to access some portion exactly like the CPU, at page fault time, that's where the access rights are resolved. So a page fault has to satisfy both the virtual memory area in terms of protection, like if I don't have read access, I'm most certainly not going to grant this page remote access, but also the access rights of the memory region. So it could be that the processor has read-write access, but that doesn't mean that I want to allow an incoming RDMA write to access that region. When something changes in the address space, it could be either because of an invalidation or because of a change of permissions. That's where we get an invalidation. So the permissions rights, again, are consistent with the CPU at all times. So when you work this way, usually what you would want to do is have, of course, access to your local process address space because you're in control. You might not always want to grant remote peers access to your whole address space. And that's where memory windows come into play, and their role and importance is becoming much higher. Because usually before you had the global address space key, you could have managed access rights to certain intervals of your address space using memory regions. But now when you have one key that has it all, you need some other mechanism. I mean, you could still use memory regions, but why not memory windows? They're a very lightweight mechanism. They're conducted directly to the hardware without any operating systems. And in fact, they could be done on the same queue, and they fence the next work request that actually use them. So essentially, when you're using the global address space key, memory windows in user space are the exact equivalent of fast registration work requests in the kernel. So as you know, we have, I think it was past year or 2 years ago, we have completely disallowed any kind of use of the DMA AMR for RDMA in the kernel. In user space, you can allow it. For example, if you have a clustered application that you trust your peers, so you can have your global address space key and grant it write permissions. But if you're doing a kind of server-client application, you probably don't want to let your clients have access to any portion of your address space. So that's where you would use memory windows. The result of this is that we basically eliminate completely the price of memory management, because we just access with RDMA any portion of the address space. We're not registering at all, other than when the application starts. Let's do a brief overview of the actual APIs to enable ODP. So we have pretty granular capabilities in the device capability. There are per transport fields, and we have bit fields for the operation that we want to do. The reason is that demand paging involves transport behavior in the HCA. So instead of opening all right up and releasing this in 2 years, we're opening gradually more and more features that support demand paging. The access flags has a new flag that's called the on demand. So basically, the only thing you need to do to register a demand paging region is just add this flag in. That's it. If you want to get the whole address space, you pass null as the initial address and FFFF as the size, and you get your address space key. If you want, you can register several of those if you want, but it doesn't really make sense. In terms of usability, so an application first gets the ODP capabilities. If you want to do sends with ODP, it checks the RC caps and send. And after that, it registers, in this example, we register the global address space key. And for that moment, there are no registrations. I mean, we could do any kind of memory allocation. I chose mmap in this case, and then post-send and give it the global address space key, and voila. No need to register memory at all. Another useful tool is the ability to prefetch paging. We've experimented with various operation models. One was to closely track the permissions of the process and mirror them to the I/O device. In our case, we're not sharing the page tables with the with the processor, so keeping them both in sync is not really the smartest thing to do at all times. I mean, if you look at the application, not all of its virtual memory is going to be a target of RDMA. So instead of that, we either incur page faults, or we can, if we know that some buffer is going to be accessed very soon, we can do a prefetch on that memory interval. After the memory is accessed, there's a good chance that no page fault will occur. So this system call is considered a hint. It might not, all the pages you requested will be paged in. You might, if you delay your access, the operating system might decide to page out the pages that you've just prefetched. Again, the pages are not pinned, so it's not under our control. The prefetch doesn't pin pages. So the use case for this is that if you have a range where you know that's going to be accessed by a lot of small transactions, you can do one prefetch for the whole range, or also for a large range. That's the idea. We have statistics that help monitor the performance of demand paging. So the main statistics are the number of page faults and the number of invalidations. They're given on a per device basis. Another interesting metric is the total number of page fault pages. In contrast to a CPU thread that encounters a page fault and you just page in that page, let's say it's just anonymous memory, not talking about IO prefetch. We have more semantic information when we're doing RDMA. For example, if I'm doing a 10 megabyte RDMA write and I got a page fault after a few kilobytes, I know this is part of a 10 megabyte RDMA write, so I can go ahead and prefetch the rest of those 10 megabytes. So we're using these semantics to get the system more efficient, and the number of page faulted pages divided by the number of page faults gives you a good estimate of the efficiency of demand paging. There are also some debug counters, mostly regarding error flows, like how many page faults the device raised with no memory region, or just statistics of how many pages we have currently paged in. I mean, this is something you can also get by the amount of memory that your process has. So, but again, for debug, it's nice to have. In terms of development, so demand paging is upstream since kernel 3.19, with all the basic support for RC, send receives, and RDMA, and also UDSend. Statistics and prefetching are not yet upstream. They're planned to come in shortly, but they are part of Mellanox OFID. One interesting thing is the notion of the global MR. It's already part of OFID 3.4, but it's going to be upstream at kernel 4.11. Memory windows are supported in MOFID. The same goes for DC, atomics, dynamic connected, and shared receive queue support is coming up, and also huge pages. So essentially, when we use on-demand paging on a region where it's mapped to the processor as a huge page, we also want to leverage this fact and map it also in the IOMMU as a huge page. Let's look at some evaluation of demand paging. First, I want to reference this paper that was published by DK's group on supercomputing last year. And they reported with MPI that they get basically the same performance with demand paging while reducing the footprint of the MPI library by over an order of magnitude. And that's huge. The second results is an upcoming paper that we're publishing in ASPLOS this year. And I'll show some of the highlighted results from this paper right now. So basically, we wanted to evaluate demand paging in 3 settings: in the HPC setting, in storage, and with TCP. So in the HPC setting, what we basically did is implemented in the MXM library. And while doing that, we just dumped over 10,000 lines of code of pin-down cache. And we tested this using 2 benchmarks, the Intel MPI benchmark suite and the effective bandwidth at benchmark. And I think the main point to note here is we have here 3 plots. The copy method, where you just copy everything into pin buffer. The green is pinning, and NPF stands for network page faults. So essentially, we have here a 2x performance improvement compared to pinning, which is kind of the brain-dead implementation. And interestingly, the page fault implementation and pinning, their lines completely coincide for all these benchmarks, and the same results go over through all message sizes and other benchmarks and MPI primitives of the Intel MPI suite. If we look at the effective bandwidth application, so first of all, we see the effects of zero copy, right? The effect of like pinning achieves an effective bandwidth of twice that of a trivial copying scheme. And interestingly, the network page fault achieves exactly the same performance. So my main point here is not really that we're improving performance. I mean, MPI wouldn't work if we didn't hold the whole working set in memory, right? But think of the simplicity to programming that's achieved using demand paging. I mean, we're just dumping all this pinning management at all. Completely. The next evaluation we did was in a storage setting. We're testing a bunch of stock Linux ISR initiators against a TGT target. And the implementation of TGT has this 1 GB staging buffer that it pins up front. And of course, it competes with the operating system page cache. The changes we need to do to the target were like 10, 20 lines of code. Just getting that staging buffer registered as a demand paging memory region. And we tested it with the FIO benchmark using both 64 and half a meg random reads. So what we did is 2 tests. The first is that we played with the amount of memory available to the server. So in the pinning case, ISR didn't even come up before we had 5 gigabytes of memory in the machine, whereas the demand paging case didn't care. And as we increased memory, the demand paging constantly had much better performance, mostly because there was more place in the page cache to cache the read workload. Once we reached a certain size, the whole disk was cached in memory, and there was no difference anymore. Now, you might wonder, why would ISR register upfront a whole gigabyte of memory for staging between the disk and the network? And it turns out that if you add more and more initiators to the target, you see even with demand paging, the memory utilization goes up, nearing 1 gigabyte. So they actually had, quite a good estimate of what they need to do. It's still less than a pinning case. Another interesting phenomenon is that the current implementation, for each transaction, it uses half a meg buffer, whether the transaction is small or large. So when you apply when you apply demand paging and test with 64 kilobyte reads, although you're allocating this half a meg buffer, you're not really paging in the whole buffer. You're just paging in the portion of the buffer that you're touching. So in this case, demand paging results in a considerably smaller memory footprint. Now, you might say that who are those idiots that written the TGT to allocate half a meg for every transaction size? And this could have been optimized instead of doing this demand paging stuff. But the thing is that I don't know and I don't care. When I'm running an application, I just want it to run good. I don't want to start controlling everybody and how they write their applications. I just want it to run with the same efficiency as it would have run using the same virtual memory optimizations that we already have. And this is the main takeaway here, right? By demand paging, we're avoiding the worst case pinning assumptions, and we let virtual memory do its work. The final evaluation that we did was implement a TCP stack over a lightweight IP and feed that stack with packets using raw Ethernet QPs. So essentially, we're kind of mimicking a virtual machine that doesn't have its whole memory pinned, which is what all hypervisors practically do today. But this could also apply to maybe container setups when you want to limit the memory of a process as well. And what we did was to evaluate the throughput of memcached servers and tested the transaction rate in a metric of hits per second. So like in the storage case, if we use pinning and we try to spawn more and more of these VMs, so to speak, after 2, we just run out of memory and we can't do anything else. With demand paging, there is no problem spawning any number of these VMs. Of course, the performance is going to depend on the actual workload that these VMs are experiencing. So, I mean, if they're short in memory, they're not going to perform very well, but you don't know that up front. As a cloud provider, you don't care what your VMs are running. You just want it to run well and maybe optimize according to the active memory in use. You don't want to do any upfront pinning. So this is kind of a static setting. When we tested the dynamic setting, what we did here is we took these memcached working sets of 1 gigabyte and we played with the payload at different times. So at one time, we have one flow that's accessing around 10% of this gigabyte, and then increasing it to 90%. And another time, another flow accesses 90% of this workload, and then kind of narrows in to a 10%. And again, depending on the applications that are currently using this memcached server. So with demand paging case, what we see is that we have optimal throughput for both of these VMs. After this transition, there is a little bit of churn where pages are migrated between the process because they're not pinned, and the demand paging system adjusts the I/O. And after that churn, we have, again, full performance. And compare that to deploying these 2 VMs with pinning, where as an administrator, you have to decide how many memory you're granting to these VMs, and in the absence of any wiser thing to do, you just take that gigabyte divided by 2 and provide half a gig for each. And what we see here, that each time the VM that's accessing the 90% is getting a 50% hit in performance. So it starts with this brown flow, and after the workloads dynamically change, there is no page migration, right? Everybody's still stuck with that half gig. And then the 10% fits nicely and gets that performance, but now the blue suffers half of its performance. So the takeaway here is that demand paging allows you to leverage virtual memory with direct I/O. Okay, so what's coming up in demand paging? So first of all, in terms of MPI support, it's already integrated into OSCO and VAPIC. In the upcoming UCX release, it's going to be supported inside UCX. In terms of upcoming applications, we want to increase the adoption of RDMA through the use of demand paging. So this could either be at the level of the runtimes. For example, think of Java JNI or Python C bindings or Go or any managed language that you don't have control on how they allocate memory. I mean, I'm never going to convince JVM guys to be prepared for allocating their objects on pinned pools because sometimes I want to use RDMA through JNI. No way, right? I just want it to work well without any changes in the JVM. Same goes for any other managed language. And then there's the whole applications. I mean, take Ceph, for example. I mean, it's a huge project with millions of lines of codes. The allocations of the Ceph buffers are done using C++ classes, somewhere 30 levels up from the communication library. And I don't want to copy in or copy out or do dynamic registration to get that Ceph workload working okay. And with demand paging, I just get it for free. When we look at GPUs, so I think practically all the main GPU vendors are now moving towards a shared address space where the GPU device memory and CPU memory are in the same virtual range. And we want to freely and transparently use RDMA to pages, whether they reside in the CPU, the GPU, or they migrate. We don't care. We just want it to work. If you look at integrations with persistent memory, so maybe our RAM wasn't that large, but with upcoming persistent memory technology, it's going to be huge. Now, think of some application that does a memory map to some file that's a few terabytes in size. I don't want to now wait for 10 minutes until I register all that. I just want, whenever I want to do like an incoming RDMA access directly to that memory, I just want it to work immediately, and when I access it, I'll use it. When I don't access it, I don't want to pay the price. Finally, we have the upcoming coherent accelerators, and we've seen in this conference the talk about C6 and CAPI. All of these guys are running their accelerated applications in the same address space as the process. I mean, the advantage to that is clear. It's exactly like the GPU case. And we want to be able to support RDMA, to transfer data and enable these accelerators without any other programming nuisance. So we have an application that's preparing some buffer to, I don't know, to flip some matrix in an FPGA logic. And I want to do an RDMA of some megabytes of that buffer and then flip the matrix. I don't want to worry about registrations. Yeah, and that's it.
So for HPC apps, I would expect that you won't see many of these page faults to happen. Is that something that you have observed as well?
Yeah, correct. I think that, well, it depends on the workloads. It's very difficult to say this is how HPC behaves, right? Because applications are really different. There could be applications that they warm up their working set, and after that, it's zero page fault. I think that's probably the majority of the case. Yeah.
Yeah. So I read the DK's paper, and I actually was surprised that they were able to use this, but they had to litter all of MPI with prefetch hints everywhere in order to get performance. So I was kind of, and I've actually worked with some of those apps that they've used, and I was kind of surprised because they were using very static set of pages, but they kept getting these faults, which were solved by adding these prefetch hints. So is that a function of the page of the IOMMU cache size, or?
It's not the cache size, but in our implementation, we're using the IOMMU and the TLB sits on the device. So obviously, it's more costly than a page fault in the processor. As we proceed and involve in this technology, we're getting better and better with lower latencies for that, but there's still a difference in cost. So I guess that it really depends on the benchmark. If you're running like a 1 minute benchmark with huge memory, and you say, and you want to page that gigabyte one page at a time, you're going to pay a considerable cost compared to pinning it up front. With true MPI jobs that last for hours or weeks, I don't think it's going to matter.
Okay, thanks.
So a lot of our systems operate under memory pressure, and so, you know, within the context of file I/O, fadvise gives you some ability to shape reclaim. Is there a mechanism like that that you believe or could use to hint, swapping activity or other things to, once you've instantiated this, to keep it where it is or to not move it around?
I think that we're pretty much trying to get out of the way of whatever policies you configure your I/O and operating system. So we're just reacting and adjusting to whatever files and memory layout you have. So there's no policy that we need to do with RDMA.
Right, but you may want to treat those regions differently if you've got a system, because a lot of systems you're really at the limit of all of the memory, and then you're under pressure. And so
Right.
This is where, in Linux, a lot of things sort of fall apart. And so hinting at some level might be pretty useful in that context.
Right. I just think that those kind of hints are not going to be involved with RDMA, but with that said, we do leave you with the decision on which memory regions to use. I mean, you can have a global hierarchy, you can have memory regions that are on demand of certain portions. You could have pinned memory regions. Let's say that you have some low latency communication going on, where you might access it once every 5 minutes, so there's a good chance that if you're not pinning, it's going to get swapped out. But you know that once you need it to be low latency, then by all means use a regular pinned memory region. You have the choice.
Yeah, I was wondering if you try to run many applications, each having its own MR, trying to cause a situation where there will be many failures when trying to access a page, and then try to see how much bandwidth do you lose.
Many failures, in what sense?
Well, you said that there is not much implication on bandwidth, right? But if you run, tens of thousands of Prefetch applications on a server, then you will probably get an increasing number of page faults, right?
Mm-hmm.
So I was expecting to see like a slide showing, okay, if I stress my system to this kind of percent of page fault, this is what I pay in bandwidth. Because I was thinking that even maybe in OpenMPI, in a large cluster, I'd get many of those.
Yeah, I think that if you're in a situation where you're running to, problems with the fit-in, the size of your active set, working set of your application running on the server, RDMA is going to be the least of your worries. If you have churn and you're done trying to do high-performance computing, you're in trouble anyway. We're not going to we're going to not improve, not aggravate that problem. So yeah, I mean, if you're thrashing memory.
Okay. Another question, not proficient that, how can there be a race between the device accessing the page and the kernel invalidating it?
Of course there is. It's an inherent race, and it exists with the CPU as well. I could say that we give priority to invalidations versus page faults, because if you're doing invalidation because of memory pressure, and because of that you might need to allocate a page of a page fault, then you could deadlock. So what could happen, even if we're in the middle of a page fault handling, and then we get an invalidation, we're not sleeping, we're invalidating the page right at that moment, and it could be that the device tried to access, got a page fault, we told it, hey, we couldn't resolve it, and it's going to get the same page fault in a microsecond.
You don't know.
Yeah, and it'll get another page fault, and then it will eventually it will resume. So it's exactly like what you would see in a CPU, where you say, if I have a very high memory pressure, and you have like a problem of progress, like the application is not progressing because it's getting page faults all the time. It's the same thing.
Okay.